we can start with the first presentation by Alba Gragera, something like this, on the gains from using action observations in domain repair. And this is a joint work with Raquel Fuentetaja, Angel Garcia Olaya, and Fernando Fernández. The floor is yours.
My name is Alba Gragera, and I'm going to present this work titled on the gains from using action observations in domain repair. As we all know, automated planning requires a properly specified domain and problem in order to get a solution plan that transitions from the initial state to the goal state. And this model description is usually written in PDDL, and although PDDL is a declarative language, creating models using it is a tedious and an error-prone task where it's easy to make mistakes. Like, for instance, we might forget to include the holding effect in the pickup action, so in this case, the planning task becomes unsolvable because it's not actually holding the block. And this is frustrating because in our mind, the planning task seems to be well specified. And we can find in literature some works trying to reduce the effort involved in the creation of automated planning models using PDDL. And in this work, we are going to focus on domain repair, that focusing on improving an already existing model to refine them and to make them more accurate and reliable. And in this work, we are going to consider planning tasks that are expected to be solvable, but for some error, the planning task is unsolvable. And the problem here is that the planner only tells us that the planning task is unsolvable without explaining why. So explaining and understanding the unsolvability of planning tasks is one of the important challenges for the planning community. And we want to contribute to this challenge by proposing an automated method to find a reparation that makes the planning task solvable. And we want this method to be general for different levels of input data provided as action observations. We call a reparation as the set of modifications that we have to make into the original domain in order to make the planning task solvable. We consider that the original domain is missing some information and is missing some domain effects, some effects in some actions, and that can make the planning task unsolvable. And in this context, we define a reparation. We define a repair as a tuple where the first element is the action being repaired, and the second element is the new effect that we are adding to that action. So this is a single repair, and a set of repairs is what we call a reparation. At ICAPS 2023, we propose an automated method to find that reparation in which we let the planning task to repair itself. And the unsolvable planning task is to compile to an extended planning task in which the solution is a plan that solves the original problem while also repairing the model. Looking into more detail to this compilation, we, of course, have in the domain the original domain actions, but in this case, they are reformulated to allow the repairs. And we introduce a set of general actions to fix a planning task. And in this set, we can find a fixed action that permanently define a fix for an action, and this fix can be either a positive or a negative effect. Apply fixed actions that apply that fix to the current state with the objects that the original domain action is using. And to close this process of the reparation of an action, we have closed actions. And all these interact together following this diagram flow that we can see here, where in the compilation we introduce some control predicates that ensure that action is repaired only the first time the action is used. It is the second use of the action or more uses of the action. It can only apply the previously defined fixes. An action can have several repairs. And if the action has already been repaired or it doesn't need reparation, the current process for the action is closed, and the compilation can instantiate another domain action, and this process follows until the goals of the problem are achieved. As I mentioned before, the solution plan contains the fixes made in the domain to achieve the goals. In this case, it has repaired the pickup action by including the new holding effect. In this compilation, using this compilation, the planner has to reason about all the actions to apply, and that's because we don't provide any input beyond the unsolvable planning task itself. And this has a limitation, and this is because the approach focuses only on making the planning task solvable. And we want to illustrate this limitation with this example that we have here, in which we have two vehicles that need to pick up all the packages to deliver them to the house, and to get there, they can avoid the mountains or cross the tunnel. But let's imagine that in the domain that we have, the action that crosses the tunnel is broken and is not actually crossing it. So our approach will say here that there is nothing to repair because the goals are still achievable by avoiding the mountains. So to overcome this limitation, we wanted to extend the approach to also provide as input in action observations. For instance, let us consider that now we want to force the solution plan to include that at some point the car must cross the tunnel. So forcing the solution to include this observation will lead the method to repair the cross-tunnel action, resulting in a better defined domain. So we extended the approach to receive as input not only the unsolvable planning task, but also a set of action observations. And going back to the Bloxworth example, let's imagine that we want to consider in the reparation that at some point the method must pick up the block A and must unstack block B from block C. These input action observations are compiled into the initial state by including the prefix OBS, and we also include some predicates to handle observations. We enumerate them, OBS 1, 2, and 3, and so on, to preserve the relative order in the application of the plan. And the goals are the original goals of the problem, but we also want to ensure that all the observations have been incorporated into the plan. So the compilation that we had before has been extended to also consider this input action observation. Now the planner has to reason about if it instantiates a new action from the domain, or if this corresponds to a domain action observation. If we remember, the action observation that we want to consider is that it has to pick up the block A, so it will follow this branch in which it's applying the action observation, which is the observation number 1. And basically, this action that we provide here in the compilation removes the activate observation, the current activate observation, and allow the compilation to transit to the next observation. And the first observation is marked as already applied. With this extension of the compilation, the approach, the objective of being general enough to consider different levels of input action observations is achieved, because if we don't provide any action observation, the compilation will follow this branch. It doesn't need to consider any input action observation. If we provide some action observations, it will combine both branches. And if we provide as input a full plan, so we have all the action observations in the plan, it will follow this other branch in which it doesn't need to reason about new domain actions, because it only has to follow the given input plan. In the experimental setting, we wanted to evaluate if providing action observation to domain repair improves the quality of the repair model. And observations are generated from optimal plans by randomly removed actions. And we provide the action observations considering the different levels of the observability of the optimal plans, where we have 0%, 30, 70, and 100% of observability for the optimal plan. And to evaluate the quality of the repair models, we have considered that we have the ground truth model. This is the domain that is really working, the domain that we have in our mind. And we use precision and recall metrics, where precision is a notion of how correct the repair model is, and recall is a notion of how complete the repair model is. And we have two different ways of computing the precision and recall metrics. In the first one, MIP, we consider that a true positive if both the predicate and the action are correct. That means that the compilation has used the holding predicate to repair the pickup action, And in MP, we consider true positive only if the predicate is correct. That means that it has used the holding predicate to repair any other action in the domain. But we think that if we know that the holding predicate is missing in the domain, in any action, it's still a valuable information. We compare our results with the state of the art, where we can find the approach by Lind et al. That is a domain learning, domain repair approach that modifies the domain to validate a given input plan, and they identify conflicts by finding unsatisfied preconditions, but the drawback is that they need complete sample plans to work, and that's why we only compare with them at 100% of observability. And we have also FAMA, which is a domain learning approach that infers action models from plan executions, and they have a similar compilation, but in this case with conditional effects. And the drawback is that they need action and also state observation to achieve good performance, while we only consider action observations. And we can see here in this table the coverage that we achieve. For each domain, the total coverage is 40. And in general, we can see that we outperform the state of the art in solved tasks. And in cases where either our approach or the other approach are not able to reach the maximum coverage, is due to memory or time reasons. Regarding to the quality metrics, to precision and recall, in the first column we have our approach, and in the second column we have FAMA. And for each of the approaches, we show the percentage of tasks solved whose precision and recall are greater than 0.75. So it's easy to see how the precision and recall values increases as the observability of the plan also increases. So the answer is yes, adding action observation to domain repair improves the quality of the repair model. And in general, we can also say that we outperform FAMA in task solve and model quality, except at 70% of observability, where looking at the previous table, they solve fewer tasks, but with higher quality metrics. And regarding the average runtimes, intuitively, the computational cost of repairing a domain, which is this part, is higher than obtain the optimal plan using the ground truth model, the ground truth domain. And also the time to compute a reparation increases as the information the planner has to consider also increases. For instance, in this case, where the planner doesn't need to consider any new domain action and it only has to follow the given input plan, the times are lower. So as a conclusion, we can say that we can have extended our domain repair approach to handle different levels of input action observation, or observability levels. This improves the quality of the repair model because we have obtained a higher quality and precision metrics. And our method improves, in general, outperforms the state-of-the-art methods because we solve, in general, more tasks and with stronger metrics. And our compilation also ensures that the repair models produce plans that are consistent with the observations while also achieving the goals. And that's all. Thank you.
Questions?
Nice talk. I remember that in an earlier version you could deal, I think the ICAPS 23 paper, you could deal with just one action trace, and I'm not quite sure whether in this work you can already deal with multiple ones, and if not, do you have an idea whether the approach can be extended so that you will be able to have multiple traces as input?
Multiple traces, you mean one problem instance or multiple problem instances or observation?
Oh, whatever you can imagine. Basically, let's assume we have the same domain but multiple, either different traces in the same problem or also even different problem instances. But the point is that if you would run if an approach would only accept a single traces input, and you run it multiple times with the same domain, you might potentially obtain competitive repairs. And I'm just wondering whether this work can already deal well with the same model just once, and if not, whether you have ideas whether this could be realized in this approach.
Yeah. The approach for a single problem instance can receive several input traces, but corresponding to that problem instance. But the current approach that we have presented is can only receive action observation for one problem instance. I know that the approach by Lin et al., which is also your approach, can receive multiple problem instances. But this one is only focused on one problem instance, which can overfit the solution to that problem instance.
But you have multiple traces, so that's already good, right?
Yeah, we have multiple traces. We have multiple action observation for that problem instance. We can deal with multiple, yeah.
What about higher level, higher language features, like, I don't know, let's say conditional effects or domain axioms? I would assume that in your approach, that should be relatively easy to realize because it's from planning to planning. Any thoughts on that?
About repairing domains with conditional effects?
Yeah, or any other higher level language feature that you could think about?
Yeah, we haven't tried with that. I mean, we haven't tried. I would say that it's easy to extend because it's only to link actions to new effects, but we haven't tried to do it. But I would say that it would be easy to extend, yeah.
Okay, thank you.
Patrick?
So I was wondering about the encoding of action observations, so specifically, if you have an observation that a certain action happens in your observed trace, when you create a plan for the modified domain, do you always match the first occurrence of the observed action to the observation, or is there a choice between matching any occurrence in the generated plan to that observation?
The first one.
Okay.
Yeah, the first one.
Is it possible for that to lead to a problem? As in, like, you actually have to do an action multiple times, and you have to match with a later one in order to respect the ordering constraints, or does that simply not happen?
I would say it's not a problem because if you have already applied that observation and it's, for instance, in this example, you have your observation is pick up block A, and you have to pick up block A several times in your plan. Once you have applied that observation the first time, it's like check, and no matter if you have to apply then several times, that action is already checked, and I would say it's not a problem. Yeah, I know what you mean. I know what you mean. I have to think about that, but I would say it's not a problem. Yeah.
That makes sense.
Yeah.
Other questions? Can you say something about could be to make your approach more effective in managing the situations in which you had a problem, for instance, with the coverage? Which are the issues that because your system was not able to fix or find a way to manage also?
Can you repeat, please?
In some cases, you were not having the full coverage of the problem, while other approaches were having.
Yeah.
Okay. Which is the limitation in your approach that prevents you to manage also that cases?
Our method is completed, so there is a solution, we can find it, and when we don't achieve the maximum coverage, it's because time out or memory.
So it's
memory
matter only of time out?
Yeah.
And if you have more time, so you are able to...
Yeah.
Oh.
Yeah, but we run the experiment with half an hour, and sometimes it's not able to find a reparation in half an hour.
Oh, okay.
Yeah,
So it's a matter of time.
Yeah.
Oh, okay. Thanks. Yeah.
Thank you. So, as in my understanding, your approach can deal with unsolvability as well as applicability at the same time.
Mm-hmm.
Is there any other approach that can do the same, or are you the only one that can solve both problems with one run?
FAMA FAMA is what I presented here. FAMA is a similar approach. It's focused on domain learning. It needs more information. It's focused on learning a domain from scratch. There is no information, but it could do if the approach also receives action observation. It could do like the same. It could deal with unsolvability and also with applicability. Yeah, FAMA could do the same, but we are higher coverage, a higher precision metric, but FAMA is doing almost the same. Yeah.
So to correct myself, it seems that these two problems can be the same thing if you're focusing on a set of action traces, right?
Yeah.
Okay.
Yeah.
Thank you.
Okay. Oh, I guess we had a lot of questions.
Yeah.
Thanks again to the speaker.
Thank you.